Yep. So this topic is something I've been interested in for the past 10 years or so. It started when I was doing a postdoc fellowship with NASA, Goddard Space Flight Center. So this work kind of spawned from there. Basically, how do you learn in real time, and what is learning to begin with? When you're learning, how do you make predictions? So this is a machine learning topic. It's going to be slightly technical. I don't want you falling asleep, so I'm going to hope to have cool demos towards the end. And also have a YouTube channel with a bunch of other demos as well. So anyways, I'll just dive right in. So yeah, I'm just going to go over this basically it's a mathematical formulation, basically a sparse distributed representation. I'm going to go over that, show the software that accompanies it, and then I'll give some examples in time series, prediction, anomaly detection. And if there's time, I even have one for learning piano music. So what is real-time learning to begin with? So basically what we want to do is we want to focus on learning spatial, temporal, frequential properties and data in real time. So you have streaming data, could be images, could be text, could be financial data, IoT data, process intelligence data, whatever. It doesn't matter as long as it's streaming and you want to do something with that data in real time. So you want to learn different spatial characteristics. You want to learn basically temporal connections, these types of things. So you don't need a lot of. So I guess one of the benefits here is you don't need a lot of large amounts of historical data. You can start learning from the first data, for first observation. Makes no assumptions about your data distribution. So this is a framework that I built for doing this, and I'll be showing you later. So basically, the nice thing about real-time learning is you don't need to be basing it on backpropagation. You don't need to learn. So typically, I mean, I'm guessing a lot of you have experience in machine learning, right? So obviously, in machine learning, you're typically finding an error and you're backpropagating that error somehow, right? Here, you don't have that. This is it's using another approach called sparse encoding, which I'll talk about. So it's highly adaptable to many ranges of problems. The only thing you need to do, which I'll show, is come up with basically an encoder. So an encoding system from the real world data to this sparse representation. Another thing too about this approach is that you don't need any fancy machine learning libraries. I built it from the ground up using Java. So every observation is taken, put into this sparse representation, and then you make a prediction. So I'll be showing that. So typically you have in like deep learning. So the deep learning phase, you have data storage. You have your batch training right here. So these squares are representing the batches. Then you have your model right here. This is usually a dense collection with high degrees of freedom, and you have to apply some regularization and stuff like that, so you're not overfitting, right? This goes into an output. You compute some distance metric for an error. That information is then backpropagated, and you continue doing this, right? So that's your typical machine learning framework. Here, what we're doing is we're taking streaming data sources. We apply a pre-encoder. This goes through an iterative sparse encoding phase, which is very fast because it's sparse. And then you have your real-time prediction. That's the basic framework here. So just give you a historical background on sparse distributed representations. It's actually it's quite new, but I would say it really started off back in 2010 with hierarchical temporal memory. How many of you are familiar with that, by any chance? Okay. So it's kind of spawned off some more research. There's a cortical learning algorithm. So this is all by Jeff Hawkins in California. So this guy goes back, talks about how you can learn in real time using sparse representations. So if you're interested more in this research, I highly suggest looking up HTM. Then there's the Feynman machine, which came out about two or 3 years ago. Similar to hierarchical temporal memory, but Here you're using a dynamic systems approach. And finally, some Hebbian learning, which is spawns from neuroscience. Also very interesting as well. So this methodology takes in some advantages of all of these approaches. So some of the advantages compared to standard machine learning, well, obviously, you know, as I mentioned, it can be done in real time, right? So you don't need a lot of historical data. It learns from the very first observation. It can run on virtually any PC, Raspberry Pi, whatever. You don't need GPUs. You don't need, you know, any of these fancy setups. It's also what's nice about sparsity is it's very immune to noise. So if I have data which has noise in it, it can learn with that noise embedded in it and find the structure, find the signal in that noise. So that's a very nice property of this. Obviously some disadvantages here. Well, deep learning methods will always be the state of the art for classification, image recognition, segmentation, captioning, all these things. It's not meant for these types of problems. It's more meant for finding signals in real time, making predictions in real time. And it really works best for sequential data. So when you have, you know, when the data is dependent on time. And also, you have to do this, as I'll show you, you have to do this pre-encoding phase. So you have to actually come up with a pre-encoder for your data. So that's one of the steps. But it actually turns out it's quite easy to do. I've already come up with many pre-encoding steps for different types of data. So a lot of that is actually pretty trivial. So now I'm just going to take a quick dive into the formulation. These slides will be available for you afterwards, so you can take a look at them. I'm just going to skim over quickly because I'd rather go into the demos. So as far as distributed representation is defined, you can think of it as a data representation where you have a width and a height and then a column. And in the column, all values are 0 except for one value, which is 1. Right? So you can think of it as a collection of one-hot vectors. So it's binary, thus normalized. Encoding using a dictionary of weights can be very fast. I mean, it's trivial. It's extremely fast. It's not dense, right? So you know exactly where your values that aren't non-zero. You just multiply that by the row in the matrix. It's also very easy to implement as well. It's actually just ends up being in the compact form, just a matrix of integers. It can be used for both structured and unstructured data. There's a lot of different easy representations you can do for all different types of data. So that's basically the formulation of the data structure that's going to be used. Then there's the next point, which is encoders and decoders, as I mentioned. So, I mean, I'm sure you know what encoders and decoders are. It's basically a mapping from one set of data to another vector space. And you have a decoder, which is the inverse of that, right? If there's no exact decoder that maps back into the original vector space, then it's lossy, right? You lose information. But most of the time, actually, you can do this with perfect inverse. You actually don't need a lossy encoder decoder. So now this method is based on a hierarchy of encoders and decoders. So basically what that means is I have, you can think of it kind of like a neural network, in fact, where you have a layer that takes information, x of t, your original data point in time, and it encodes that information into a hidden space, a hidden state, which is also sparse, right? That thing gets mapped into another encoder, and so forth. It goes around in this hierarchy, this system, and while it's going up, you're extracting spatial information, more intrinsically to the data. So the dimensions here are much bigger than the dimensions here, much bigger than the dimensions here, so forth. Going around, this is the decoding phase. Now I'm doing the opposite. I'm decoding that information back into a prediction. So the input here, the output here, is the prediction for the next timestamp. So, but how are you actually encoding this image? How do you actually learn, right? So that's what we're here for. So the learning is actually done by sparse encoding, which goes back to about 2006, I believe. And basically what you do is you try to find, you define a residual error between your sparse representation and what your representation of what the actual data point is. And you compute this residual error, and it's propagated in each iteration. There's the algorithms here. I'm not going to go over it in detail. The slides will be available for you. But nonetheless, you get basically a projection onto the error space. This projection is then propagated, and then you take your basically your biggest values. You encode that as a one-hot vector, and then you compute your residual there. So this is basically the sparse encoding of the column space for the representation. You're then updating your dictionary based on a linear updating formula. For the prediction, same thing, but now you take the transpose of your dictionary weights, and you get, for the decoding phase, then your prediction for your next observation. So now, how do we learn in time, though? So that's for the spatial representation, right? So how do you learn in time now? So here, what you want to do is actually create a structure somewhat like this. If you're familiar with clockwork recurrent neural networks, this is very similar. Basically, the layer structure that I showed earlier, what you're doing is you're connecting it in time backwards. So at your highest layer, that's actually going to be dependent on a layer, the highest layer, 4 time steps ago. And then your layer before that, that's dependent on the layer 2 time steps ago, and so forth. So you have this exponential, it's called an exponential memory. And basically it's, as you are going up in your layers, they're going to be dependent on the most abstract signals that were found in the data from many time steps ago. Your lower layers are going to be more dependent on the layer before. So this exponential memory idea is not new. It goes back to the clockwork recurrent neural networks. So I just stole that idea and used it here. Turns out to work pretty well. So this is the whole entire package together. You have your real world data right here. It could be images, sequence of images, time series observation, text, whatever. That then gets encoded into this sparse representation. For each of your, so if you have multiple components of your data, like a timestamp plus a vector of real numbers plus whatever, categories, whatever, each of these are represented as an input layer. So you would have time here, vector number 1, vector number 2, etc. Then this gets put in the representation, the hierarchy shown here. And you make your predictions. You have your decoder that gets projected back into the real world sequential data if you want, and then it cycles through. So with your first observation, you don't need any historical data. With your first observation, you can make a prediction. So just with one observation, I can already make a prediction of what the next observation is going to be, knowing nothing about the data. I mean, it's not going to be a very good prediction, but nonetheless, it's still a prediction. I've compared this with RNNs, just basically looking at accuracy, time. Because of the sparse nature of it, I don't have to do back propagation, I don't have to do regularization, I don't have to do all these things. It's very fast. So time-wise, it executes very quickly. Also in accuracy, it beats out gated recurrent units, long short-term memory, etc. So I'm going to actually show, because it probably is better, I should start showing now, the the software in action here. So this is all written in Java. I'm not an amazing coder, but you know, I use JavaFX for the user interface. So what you'll see here. So for this first example, I'm going to show a sequence of time series, which you can think of like maybe signals from a power grid. They have outliers in there, so there's going to be, you're going to see some jumps in there, some spikes. And so what it's going to do is it's going to start learning. So it knows nothing about the data, and it's going to start. It gets a first observation. It's going to make a prediction. And then it keeps on getting new data, and you'll see how it starts to converge to the original data, making a prediction each time. And it captures the outliers as well, as you'll see. And on this side right here, what you'll see is the sparse distributed representation of the first layer. So I'll go ahead and... So obviously it looks pretty bad at first. Yeah, the predictions are kind of all over the place. I guess I should put some music in the background or something. I don't know. But you'll see after about a minute, it'll start to get better. But right here, you see how the predictions are. This is the first layer of the hidden state. I mean, it doesn't make sense to you probably because it looks less like random dots, but what it's doing is it's taking, so, I mean, obviously with this data, there's, you know, billions of different combinations you can have, so the dimensions there are very large. So I'm taking that dimension and now I'm putting it in a 4x4 matrix of integers of between the numbers 1 and 4, or 0 and 3. So you can see already it's learned basically this basic sinusoidal wave. That's pretty trivial. You can see on this, I don't know if you can see it back there, but there's a kind of a magenta colored line. So that one's almost converged. And you'll start seeing now that that it's starting to predict the outliers. So basically the jump outliers.
Could you show the outliers? It's not obvious.
Yeah. So you see how this green goes like this, and then suddenly there's a spike down. That's a discontinuity in outlier.
Okay.
For example. For example, right here, I don't know if you can see it or not.
Same type of outlier or discontinuity what has been seen before, sort of. This sort of pattern.
Yeah. Right? So the length of the discontinuity, the jump, is basically that's basically randomized. The outlier though is seasonal. So it learns the temporal. Knows kind of when there's a high probability of an outlier, and it will make a prediction based on that. So it's encoding not only the time series data, but also the time itself, the timestamp itself. So it's learning, you're learning information from the time. So for example, this was daily data. You know, you're getting data Monday through Friday, and there's Sunday through Saturday, and there's a high probability on Saturday that there's an outlier. It makes it learns the probability that there's an outlier on Saturday. So that's one advantage. So that's one of it. I mean, typically when you're doing time series, so machine learning and time series, you care about your vectorial data. You care about the time. You care about the actual data, but you care about the lags. But you're never encoding time information, temporal information. You're never encoding, say, oh, this is a Saturday. That's typically never done. But here you have a direct approach of doing that. You can take that time observation and encode, say, the day of the week into a value between 1 and 7, right? The hour you can make between a vector, one hot vector between 0 and 23, etc. So you can encode that information in here. One last thing, so you can see right here how you have a jump outlier right here in the magenta colored line, and it's predicted that. So now I can make, so this is these are the predictions of the data for the next 100 or so values, and it predicts that there's going to be an outlier there, and so forth. So now before I end, because I just have a minute left here, I wanted to show you, it can also do naturally built image encoders. So, how much time do I have left? Okay.
Does it also work with multivariate time series, or is it just
What's that?
multivariate, or is it just univariate?
This is I'm showing 3 time series right here, so this is multivariate.
Yeah, but there's not 3 that influence 1. They are all independent.
Yeah, it's 3 time series, and it's making 3 predictions for each time series.
Right, so it's 3 univariate time series.
I don't understand. It's multivariate.
Do they depend on each other? Like if you
No dependency on each other.
That's what I was referring to.
I mean, you can make it dependent on each other by just encoding all that information into one input layer, but I'm having 3 separate input layers, so I treat it as 3 separate time series. And so I make no assumptions on the spatial dependencies or the temporal dependencies on these. But I could, yeah. All right, so I guess we're time for questions.
Yeah, I think we can accept one question if there is any more discussion you guys want to have with Christian. Is there any? Yeah.
Maybe I don't need a microphone, I don't know. I have a question about the outlines you showed. If they were spaced further apart from each other, I guess your number of layers would not have sufficed to capture this kind of temporal structure, is that correct?
Well, I think I was using 5 layers here, so I mean it doesn't really matter. So the outliers are learned by when they occur. So usually I would have it say on there's a high probability. I would give a probability, 80% probability on a Saturday that there's going to be an outlier, and it tries to learn the frequency of this. So it doesn't assume anything about any outliers. It doesn't even think there is an outlier.
Okay.
Is that,
okay, thank you very much.
I don't know how to answer that.
Yeah. So I think PwC has also a stand downstairs. Maybe there is Christian will be available for further discussions. Visit him at the booth so that you can probably learn a bit more from that. So thank you very much, Christian. There's a small present for you that you can clap.
Okay.